Good morning. This is nuclear plant mechanical components. So we will pick up where we left off with pumps. So at the end of the last lecture, we started to break down our discussion of pumps. So as a recap, a pump is a device that uses an external source of energy to move fluid from one place to another. We define capacity, the term capacity, which we can define as the rated volumetric flow rate. For a given set of parameters. And we said we normally express the capacity units gallons per minute or cubic feet per second. So then we started getting into head calculations, which required us to talk about pressure and pressure head and how to calculate columns of pressure, things of that nature. So let's bring that back to the front. So a column of fluid, air or say liquid, gas or liquid, creates a pressure at the bottom of the fluid due to the weight of the molecules pressing down on one another. And we said the pressure can be determined by the equation P for pressure equals rho, density, G, which is the gravitational acceleration, Z times Z, which is the height of the column of fluid in question, over G sub C, which is the gravitational constant. So we gave an example of how to convert 1 foot of water into units of pounds square inch, PSI. Let's write it this way first. Pounds force per square inch. So given water, we said we know the density rho of water, 62.4 pound mass over feet cubed. Density is mass per volume. We know G in US units is 32.2 feet per second squared. It said convert 1 foot of water. So that means the height of the column Z is 1 foot. And we know our G sub C constant is 32.2 feet pound mass over pound force second squared. So setting this up to solve for our P, which we said is rho GZ over G sub C, you have 62.4 pound mass over feet cubed times G, 32.2 feet per second squared, times Z, which is 1 foot, over G sub C, which is 32.2 feet times pound mass over pound force second squared. So as units cross out and you do your math, you're left with the pressure of 1 foot of water is 62.4 pound force over feet squared. This makes sense because our unit is force per feet squared, force per area. And we know pressure is force per area. So it works out. The units make sense. But the question asks not in pound force per foot squared, but PSI, pound force per inches squared. So we have to convert the units. So we said P is equal to 62.4 pound force per foot squared. And we know 1 foot is 12 inches. So 1 foot squared is 12 inches times 12 inches. That's our conversion factor. 1 square foot is 144 inches squared. Feet squared cross out, leaving you pound forces per inches squared. So this gives you approximately 0.433 pound force per inches squared. Then we covered open versus closed pumping systems. In that open system, we define as where the system takes suction from one source and pumps the fluid to another source. Whereas a closed system is isolated from the environment. Pump suction. When a fluid is pumped, the fluid must be available at the inlet of suction of a pump. And like, as we said previously, a pump works by moving a volume of fluid. If the fluid level is below the pump suction, the work has to be performed to move the fluid to the suction of the pump. If the fluid level is above the pump suction, the fluid has the potential energy and no additional energy is required to move the fluid to the pump. Let's take a look at what we mean by that. So here, where we term suction lift, is the source to be pumped is below the pump, whereas suction head, the source to be pumped is above the pump. So in this image here, suction lift, this is the pump, this is the source. So energy is required to pump the source up to the eye of the pump and then send it to wherever the pump is going. In the suction head example, the source is above the pump and the energy or the potential energy is enough for the liquid to reach the pump. So the suction lift versus suction head. So lift, source fluid below pump, head, source fluid above pump. So typical units we use here are feet or feet of water, like we just calculated, which we said are equivalent to PSI. They're all pressure units. So static suction lift, once again, keyword here is lift. So the source fluid is below the pump suction. This is defined as the work required to lift the fluid to the eye of the pump for a given set of conditions. So here, suction lift, this is the pump, the source to be pumped, this is the suction side, is below the suction side. So we have to exert some energy to get the fluid up to the pump so we can discharge it wherever we need it to go. So let's define some terms that are used when we're working with static suction lift. we have an H pressure term. This is the height due to pressure on fluid. So in this case, it would be the atmospheric pressure. Since this system is open, it's the atmospheric pressure that is being applied to the system. And typically atmospheric pressure, you can assume units of 1 atmosphere. And 1 atmosphere is equivalent to 14.7 psi absolute, or 1 atmosphere is 33.9 feet of water. Another term here, H fluid, this is the height of fluid level. This term H sub I is the height of the eye of the pump. The eye being the pump center line. So we can then calculate our static suction lift. We'll call that lowercase a lift H pressure plus our H fluid minus our HI. Let's do an example. Here the problem wants us to calculate the static suction lift for the system below. And it says both tanks are open to atmospheric pressure, which we said 1 atmosphere, right? Or 33.9 feet of water. Here we'll be working in feet when we're doing these head calculations, just for ease. So static suction lift, we're talking about this section of the problem, right? Lifting from the source to the pump. So once again, our H lift static, our static suction lift is H pressure plus H fluid minus HI. So our H pressure, we said both tanks are open to atmospheric pressure. So atmospheric pressure is 33.9 feet. The height of the fluid is given here, 580 feet. Now, the HI, or pump suction center line here, was given to be 592 feet. So we're 33.9 plus 580 minus 592. Our static suction lift is 21.9 feet. Now let's introduce a new term, velocity head. So pump, we said, moves fluid, which means this fluid has a flow rate and which means it's moving, so it moves at a certain velocity, which is like speed. So velocity head is the work required to maintain this velocity. So the velocity head is equal to the height the fluid would reach due to its kinetic energy. The velocity head will always be a positive value if the fluid is moving in the right direction through the pump. So now total suction lift is the sum of the static suction lift, which we just calculated, the sum of the static suction lift, the velocity head, and all frictional losses in the piping and fittings. The object of this calculation is to determine the pressure developed at the inlet of the pump. So the total suction lift we'll define as H lift total is equal to our static suction lift plus our velocity head minus our frictional losses, H loss. Let's do an example. So here we're going to calculate the total suction lift for the system below. And once again, we're talking about this here, lifting from the source to the pump. Using this equation here, we're going to determine the total suction lift. And both tanks are open to atmospheric pressure once again. So in the previous problem, or the previous part of this, we calculated our H lift static, or our static suction lift, to be 21.9 feet. Same problem, we calculated that aspect already. So our total suction lift, H lift static, which we already calculated previously, to be 21.9 feet, plus our velocity head, which is given 1 foot, minus our frictional losses, which is our frictional head here, 2 feet. So our total suction lift, 21.9 feet plus 1 foot minus 2 feet. One thing to mention and keep in mind, when you're selecting a pump for a specific system, the system must be evaluated for 2 conditions. These are the lowest free fluid level possible during normal operations and the lowest pressure applied to the fluid. In addition to understanding the frictional losses in the piping, velocity head, things of that nature. Okay, let's go to suction head. So we said when the source fluid to be pumped is above the pump, we refer to this as head. So we have static suction head. And this is the energy available due to the actual vertical distance between the fluid level and the eye of the pump. As well, and includes the pressure exerted on the fluid surface, which we know in the open system is the atmospheric pressure. So static suction head. Once again, we know this H pressure is the pressure exerted on the fluid surface, in this case open system, atmospheric pressure, which we take as 33.9. We have our H fluid again. Which is the height of the fluid level. And of course, our HI, which is the height of the eye of the pump. So H, static suction head. Remember, head, the source, is above the center line, as opposed to lift when the source is below the pump center line. Here, static head, above. So my H static suction head is the H press plus the H fluid minus the HI. So let's do an example. Calculate the static suction head for the system below. Both tanks are open to the atmosphere, so at atmospheric pressure. We set our static suction head. So here we said atmospheric pressure. So H pressure is the 33.9 feet. The height of the fluid here, all right, we're on the suction side of the pump, this side, is 604 feet. And the IV pump here is 592 feet. So my static suction head is 45.9 feet. So then my total suction head is the sum of the static suction head the velocity head, which we defined previously, and any frictional losses. So my total suction head, A suction total, is my static suction head plus my velocity head minus my H frictional losses. So here, we want to calculate the total suction head for the system below. We previously calculated the static suction head. We determined that to be 45.9 feet. So the the total suction head is 45.9 feet plus my velocity head, given here, 1 foot, minus the frictional losses, or the frictional head given here is 2 feet. So my total suction head is 44.9 feet. Now discharge head. This is defined as the total energy of the fluid at the discharge of the pump. So we have static discharge head, symbolized by uppercase L uppercase L sub D, lower subscript capital D. And this is a measure of the height or discharge level above the eye of the pump inlet. In addition to the pressure exerted on the fluid, which in the open system we're saying is the atmospheric pressure. So here we're now talking about the discharge side of the pump. So the discharge head, the height above the eye, this is the eye, to where the fluid is discharged into the receiving basin, receiving source, we call receiving basin. And we define that as the static discharge head is the H pressure plus the H, or the height of the fluid discharge location, minus the HI. So let's do an example. Calculate the static discharge head for this system right here. And once again, now we're talking about this discharge side of the pump. So once again, both tanks are open to atmospheric pressure. It's the key word there. So atmospheric pressure, we said, is 33.9 feet of water. The fluid discharge level is 617 feet. The height of the eye, minus 592 feet. So the static discharge head, L sub D, and just like on the suction side, there's a total discharge head, which we include static discharge head, velocity head, and our frictional losses. So our total discharge head H discharge total, static discharge head plus velocity losses plus frictional losses. So if we calculate our total discharge head for this system right here, recall in the previous example, we've already calculated our static discharge head. To be 58.9 feet. So total discharge head plus our velocity losses, which we said is 2 feet, plus our frictional head, which is 4 feet. So our total discharge head is 64.9 feet. And let's talk about total head or total dynamic head. This is the difference between the pressure of the discharge side of the pump we call the total discharge head which we just calculated, and the pressure on the suction side of the pump. Which is the total suction lift if the source is below, or the total suction head if the source is above the pump. So the total head, abbreviated TH, is the pressure of the discharge side minus the pressure of the suction side, the pump. So is the H discharge total, or the total discharge head minus the total suction lift, or total discharge head minus the total suction head. So here, on the suction side of the pump, we're talking about lift because the source is below the suction, and this is the discharge side. So the total head is getting the pump, the fluid from the source level to the discharge level. So once again, total discharge head, total head is the total discharge head, in this case, minus the total lift head. And in this case, where on the suction side, the source is above the pump suction, so this is suction head as opposed to suction lift, the total dynamic head is the total discharge head minus the total suction head. Let's talk about something similar, something new. So we defined cavitation previously. Let's refresh ourselves on that definition. And we said this was the formation of bubbles in the low pressure region of the pump and their subsequent collapse in the high pressure region. Cavitation can occur in both centrifugal pumps and positive displacement pumps. cavitation damages pumps due to erosion and pitting. These are corrosion terms that occurs the vapor bubbles collapse. So we should prevent, so cavitation should be prevented. So let's introduce term net positive suction head. So to prevent cavitation, which we just said should be done at all costs, the pump must have some minimum positive pressure at the pump suction. The difference between the pump inlet or suction pressure and the saturation pressure of the fluid being pumped is called the available net positive suction head. So if the available net positive suction head is not greater than required, the pump will cavitate. So to calculate the net positive suction head at any point in the system equals the suction pressure minus the saturation pressure of the fluid being pumped times a conversion factor, G sub C over rho, which we say is the density of water, times G, the gravitational acceleration, which is basically a unit. This is a conversion thing. Let's define pump efficiency. So in real pumps, not all the power that is supplied to the pump is converted to head. So the efficiency of the pump, defined as this term, is defined as the ratio of the work required by an ideal pump to the work required by a real pump. An ideal pump is a pump in which all work is converted to head. So the pump efficiency is equal to the useful pump power over the input pump power. So the difference between the input pump power and the useful pump power that is actually converted to pressure or head is the power loss to friction in the pump. This energy is converted to heat and is carried away by the fluid. So let's talk about the two different types of pumps. We have positive displacement pumps. These pumps deliver a fixed volume of liquid for each cycle of the pump. So with each cycle of the pump, the same volume of liquid is displaced regardless of changes in the system flow resistance. So the resulting volumetric flow, remember GPM or cubic feet per second, is constant. Positive displacement pumps, PDPs. So positive displacement pumps are typically used in systems that require a constant flow. PDPs, positive displacement pumps, can be grouped into two basic categories. You have reciprocating pumps, and you have rotary pumps. Three main types of reciprocating pumps. You have piston type, plunger type, and diaphragm type. Three main types of rotary pumps. You have the gear pump, vane pump, and screw pump. Reciprocating pumps are named based on their action. So they feature a cycle, which is a movement back and forth within cylinder or casing. So it's the same motion back and forth, back and forth. So if you have a casing and a piston, and this is the volume of the casing, that piston is going this way, coming back. The same motion, back and forth, back and forth. So it's a back and forth reciprocating motion, hence the name. Rotary pumps have gears, vanes, or screws that rotate to move fluids. So an example of a reciprocating positive displacement pump, you have the fluid that enters in this through this valve right here into the chamber. So fluid is coming this way right here. This is the piston right here. Piston goes back and forth. So when it's all the way back and it's on its way back, the pressure in here decreases, which allows fluid to enter the chamber. So once it finishes its cycle to the back, it then goes forward, thereby pushing the fluid through the discharge or outlet valve here. So as we said, is positive displacement pumps is the same volume of fluid per cycle. This volume inside this chamber here does not change. The only thing that can change it is the stroke length of the piston here. If the piston stays stopped here instead of stopped here, then your volume changes. But wherever it is, the volume on each cycle remains the same. So if the fluid coming in and the fluid going out for each cycle of the piston. So thereby, with these reciprocating positive displacement pumps, the volumetric flow rate of the pump depends on the volume of the cylinder or chamber and the speed of the pump. So changing the speed by which this piston moves can increase your volumetric flow rate. Reciprocating pumps are self-priming. This means that if there is air in the suction line of the pump, the pump will draw the air into the pump and discharge it into the discharge line. This does not mean that you do not have to follow procedure to fill and vent the pump. Now here is an image of a double acting reciprocating pump. So as the piston cycles back and forth, goes here and comes back here, as it moves to the right, inlet flow can fill up this side of the chamber. And as the piston slides to the left, well, let's stick to the right. As the piston moves to the right, inlet flow can fill this side of the chamber. But as it moves to the right, it's pushing the fluid that was in this side of the chamber out and discharge. Now, once the piston slides back to the left, the fluid that was over here in this side of the chamber can now discharge, and then fluid can enter back in this chamber. So it's a constant, as opposed to the previous image where it was one chamber and is in and out. Here in this double acting, as it slides, fluid inlet can come here, go out, and it's come back this way through the cycle. It can flip the other side. So this is called a double acting reciprocating pump. So double acting it discharges fluid on both strokes of the piston. So rotary pumps is a positive displacement pump that employs a rotary motion. These pumps are also self-priming due to their ability to remove air from suction lines and produce a high suction lift. Rotary pumps typically operate at low speeds in order to secure reliable operation and maintain pump capacity over an extended period of time. Gear pumps are the most common type of rotary pump in industrial applications. So the gear pump here consists of two gears, two spur gears, meshing together and revolving in opposite directions within a casing. So this gear is rotating this way, and this gear is rotating that way, opposite directions. And here the inlet fluid enters here, and it cycles around between the gears and the casing and exits here. With the large number of teeth usually employed, on the gears, the discharge is relatively smooth and continuous with small quantities of liquid being delivered to the discharge line in rapid succession. Screw pumps are used to pump oil or other viscous, well, I should say that better, or other fluids with high viscosity. And we know viscosity defined as the measure of the resistance of a fluid to flow. As in, syrup is more viscous than, say, water. Vane pumps are used to move hydraulic oils, lubricating oils, solvents, or chemicals. Diaphragm pumps write that a little different. The diaphragm pump advantages include the elimination of any contact between the liquid being pumped and the source of energy. This eliminates the possibility of leakage, which is important when handling toxic, radioactive, or very expensive liquids. Disadvantages of diaphragm pumps include limited head and capacity range, some safety precautions of positive displacement pumps. A positive displacement pump should never be started with the discharge blocked or the discharge valve closed or throttled. And throttle meaning partially closed. Additionally, the discharge valve should never be closed or throttled when the positive displacement pump is running. Positive displacement pumps are normally fitted with relief valves to protect the pump and its discharge piping from overpressurization Characteristics of positive displacement pumps. So this is a pump curve for a positive displacement pump. So for a positive displacement pump, the volumetric flow rate is directly proportional to the pump speed. The capacity, volumetric flow rate, remains virtually constant for any discharge head So in this pump curve, the x-axis is the volumetric flow rate, the y-axis is the total dynamic head. This pink line is the operating curve here. So due to the relationship of flow rate and pump speed for a positive displacement pump, doubling the pump speed doubles the volumetric flow rate. So if we say V is volumetric flow rate in whatever units you want, gallons per minute, gallons per hour, etc. And we define N in pump speed, revolutions per minute, RPM, then we can say V2 N2 over N1 times V1. So basically, with the directly proportional relationship between pump speed and volumetric flow rate, if V1 is my initial pump speed and N1 is if V1 is my initial pump flow rate, volumetric flow rate, and N1 is my initial pump speed, if I increase the pump speed or change the pump speed, my new volumetric flow rate is directly proportional to it, per this relationship. Centrifugal pumps. These are the most common type of pump used in industry. They impart a rotary kinetic energy to the fluid, which is the centrifugal force, hence the name. So centrifugal pumps create flow by moving the fluids faster and faster in a circular motion and then changing this increased speed of the fluid into pressure. They are capable of a wide range of pressures and flow rates. We'll stop here in this lecture and pick up here next time. If there are any questions, please feel free to email me, and good luck.